Okay, so today's topic is this thing called elastic potential energy. It's energy that's actually stored in an object that we would call elastic. Elastic just simply means that it would tend to return to its original shape once I stop pushing on it or pulling on it. So there's a lot of things that would be considered elastic, really anything that would just tend to come back to its original shape. Springs are very common examples. Tennis balls are good common examples. Even the strings that make up the part of this racket are what we would call elastic objects. And golf balls, certainly you've probably seen that golf balls are highly elastic. So when we do work on compressing or stretching something that's elastic, we actually store energy in that object because it's a deformed shape, due to its deformed shape. The object's going to have a tendency to go back to its original shape, and when it does that, it can do work by applying a force through a displacement. So the same basic idea here on how we define elastic potential energy. I often abbreviate that as just EPE, and I think your book might do something similar. But the work, or the energy stored in elastic objects is equal to the work done in changing the shape. So you push down on that spring with a certain force F, and you push it down through a certain displacement. If I were to multiply those two quantities together, I would get the amount of work that's I do on that spring, and that would be stored energy. That then could do work on something else. Maybe if I put a ball on top of that, it would shoot that ball off. Now, that's sort of a simplistic view. As we said, work is equal to F times D times the cosine of theta. And that's true as long as the force is constant. Unfortunately, for elastic potential energy, the force is actually variable. It actually increases the further I stretch that. That's probably most easily understood by thinking of a bow and arrow. When you pull back on that string on that bow, the beginning portions of that, the beginning portion of the pull is very simple. It doesn't take much force to be able to pull it back, maybe 2 or 3 centimeters, and then the next 5 or 10 centimeters, it's even harder to pull back. And a lot of times, if a bow is really tightly strung and it's really hard to pull it back that full distance, sometimes people can't actually get it to full draw because the force actually gets progressively harder, or it actually gets progressively harder to pull it back. If I were to graph a force versus displacement curve for that, what you would see is that the force actually increases pretty linearly with the displacement, and so I'd get a nice little straight line. Now that straight line has to do with how we quantify elastic potential energy. The equation that we would use to quantify EPE is really just 1/2 kx squared. We'll talk about each one of these terms, and we're going to have to do a lot of things in class to try to make sense of this. EPE is definitely more difficult to understand than GPE. And again, a lot of it has to do with the spring constant and that squared distance. The SI unit is a joule. It is a scalar quantity. It can be only positive or zero. It can't be negative. Displacement could be in the negative direction. Like, for example, we could compress that or pull it and have x be either positive or negative. But when we square a number, it doesn't matter what it is, either positive or negative, it will always be positive, and k is always positive. So EPE would only be positive or zero. Remember, GPE could be negative. Now, the spring constant K is really just, it describes the relative stiffness of the object. The stiffer the spring, or the tighter those strings are here, or maybe how hard that golf ball is to compress, that's all related to that value of K. And so it's really just the slope. What it is it's the slope of this force versus displacement graph. A really high value of K would mean that it would be a steeper graph. It would take more force to stretch it or compress it a given distance. And a lower value for K, if I had something that was fairly weak, it would have just a lower slope here. And so this would be a smaller K value. Again, we're going to do lots of things in class to try to make sense of that value. The delta x is how far it's stretched or compressed, and probably the key thing to look at right now is that the elastic potential energy is related to the square of the distance. So we store more and more energy for every extra amount that we pull that back. We actually store progressively more energy, so it's related to the square of the distance. Said another way, if I pull that bow back 10 centimeters, I might store, let's say, 50 joules of energy. If I pull it back another 10, so if I pull it back to 20 centimeters, I don't store 100 joules. What I would actually store then would be 4 times the energy. So I would actually get that up to 200 joules of energy stored because it's related to the square of the distance. And we've seen that with speed, kinetic energy equation too. If you double the speed, you end up getting 4 times the kinetic energy. Same thing here. If you double the displacement, you end up getting 4 times the energy. So an egg launcher is made with elastic cord of strength 75 newtons per meter. It's pulled back a distance of 145 centimeters and then shoots a 72-gram egg. I'd like to first know how much EPE is stored in the cord prior to release. And let's assume it's a slingshot design, so there's 2 bands stretched. The first thing I want to do is I just want to determine the energy stored in one of those bands. To do that, I'm just going to use the equation for elastic potential energy. E is 1/2 kx squared. In this case, the energy stored in that band would just be 1/2. The spring constant is 75 newtons per meter. We'll look at that unit more in class. But that's the relative strength of that particular cord. And I'm pulling that thing back 145 centimeters. And I'd like to put that in meters so that I get the SI units for it. And I'm squaring that. Let's go ahead and compute what that energy is stored in that band. And I'm getting that to be about 79 joules. I think I get like 78.8-ish or so. Now that's the energy stored in one band, so I'm just going to say that's per band. And in this case, because I actually have 2 bands, I have one on this side and then I have another one up here. Well, the total energy stored would just be 79 times 2, since I had 2 of those bands. And so that would be what, 168, looks like 168 joules of energy stored in the elastic cords. And of course, wouldn't it be nice if I could actually do the math here in my head, which apparently I can't. It's actually 158 joules, so let's check that. And that would be the total energy that's stored in those bands. That happens to be equal to the work that I did. That would be equal to the work that I did in pulling back the work done by me. So that would be equal to the work I did there. Yeah. Now, assuming the cord does the equivalent amount of work on the egg as it returns to its original shape, just how fast would that egg get shot out from that launcher? So you just stored energy in those cords. Well, that energy can go back out into the egg as the egg launcher sort of launches that. So let's go ahead and set the kinetic energy of the egg equal to the work that I did in pulling back those bands. Well, that would be equal to 1/2 mv squared, since it starts from rest. And I'd like to just solve that for the velocity of that egg. So to do that, it'd be 2 times 158 joules. And then I'd have to divide that by the mass of the egg. And the egg in this case is 72 grams. I'm going to put that in as a 0.072 kilograms. And then that would be equal to v squared. And I'd again have to take the square root of that in order to get to v. And so that value, I'm not going to try to do this one in my head, since obviously I can't do this kind of calculation. So let's go ahead and let me use the calculator for that one. And what I'm getting for that speed is about 66 meters per second. And again, this is just a way for me to show you how elastic potential energy gets converted into other forms as well. So now I'd like to show you an example where we could determine the spring constant for a spring, and this is how you typically do it in a lab, in a laboratory session. We'll do something like this in class as well, so you can see it firsthand. So what I have here is a spring that I'm going to hang from a rigid post, and so typically we just draw something like this here. And so I have a spring, and it's got a relaxed length. We set at 12 centimeters. So when it's just dangling there and there's nothing hanging from it, it's 12 centimeters in length. That's what we call its relaxed length. Now I take a 250 gram mass, and I hang it from that. So I'm just going to go ahead and draw that here. When I hang that off of that spring, it's going to stretch it, and it stretches it because it's exerting a force. That force that it's exerting is equal to the weight of that object. Let me just go ahead and draw that spring now actually stretched here. So it stretches down to a total length of about 59 centimeters. And so here's that mass hanging from it, and the new length is all the way down to 59. Now, what I'm interested in doing is just determining the spring constant. So to find the spring constant for this, the equation that we would use for spring constant would just be F over X. K is really just defined as a ratio of the amount of force it takes to stretch the spring a given distance X. So when I take the ratio of those, I get the spring constant. Now, if we think about the force that's acting, that's required to stretch that spring a given distance, I'm just going to draw a quick FBD for that mass down here. That's the weight force, equal to m times g. That's the force from the spring. And I can see that that force is this value up here. It's equal to the weight of the object since it's in a state of equilibrium. So the spring constant could be computed as equal to mg in this case, the weight force that's acting downward. And the x value is really just the difference between the relaxed length and the new length here. So that'd be 59 minus 12 centimeters, and I would like that to be in meters. So the numerator becomes 2.45 newtons is how much force is acting to stretch it. In this case, the stretch distance, it looks like it's 0.47 meters. And so when I take that ratio, I'll get something called the spring constant. And let's go ahead and compute that. And that value turns out to be about 5.2 newtons per meter. Now, that value just tells us how much force is required to stretch it a given distance. If you want to think of it like this, if I exerted 5.2 newtons of force on that spring, I would stretch it 1 meter. If I exerted 10.4 newtons, that would stretch it 2 meters. It just tells us a ratio, again, of force to displacement. And since it's a constant value, that constant value is actually equal to the slope of that f versus x graph. You can see that I have a linear relationship between force and displacement. Linear relationship can be shown with the equation written this way, where f is equal to kx. This is very similar to an equation of a line. Y is equal to mx plus b. This is the force is equal to kx, where k again represents that slope. Now I'm also interested in determining the energy stored. Well, the energy stored for a spring is just going back to our EPE equation, 1/2 k delta x squared. And so this case, since I now know the spring constant, I can go 1/2 times 5.2 newtons per meter. And when I multiply that by how far it's been stretched, again, that stretch is 0.47 meters. And when I square that 0.47 meters, I get this value for the elastic potential energy once I multiply them out. And that's about 0.57 joules. Not a lot of energy, but it certainly does have energy, and I could see that if I took that mass over there and just let that spring go, it would shoot up this way because it's got a lot of elastic potential energy, and that elastic potential energy can be converted into other forms, which is what the next example is going to show. Okay, now our final example I want to go do with you for elastic potential energy is dealing with a bungee jumper. And again, this is a good segue into our bungee lab that we're going to do. So this is just a problem that would be showing you energy transformations and what kind of energies are present during a bungee jump. So we have a 75 kilogram person that's standing on top of a bridge with a 20-meter long bungee cord attached to his ankle. So let's just go ahead and let me get a person there for us so we can sort of visualize this. Okay, so there we go. Let's go ahead and place him up here. And I think what I want to do is I want to show the actual cord here. So we have that cord that's attached to his ankle, and it's 20 meters long, so it's going to be in a loop there. So he's going to go ahead and jump off of this bridge, and that bungee cord is going to start to stretch and store some energy in its shape. So the bridge is 60 meters off the water below. Let's go ahead and draw that here. So there's the water. When the jumper reaches its lowest point, the cord has stretched 20 meters from its relaxed length to 45 meters. So you'd be way down here at that point. Assume the cord behaves like a spring with a spring constant of 85 newtons per meter. So a fairly strong cord. First thing I want to do is I want to use the work net is equal to delta KE theorem to determine the speed of the jumper when the cord is just about to stretch. Let's just show where that is. So here he is. He's going to be upside down now. So let's just turn him like this. He's at this particular point. The cord now, let's just redraw that. The cord is actually hasn't stretched yet, but there he is. I would like to know how fast he's going at this point. So I just like to know his speed at that point, and the way I'm going to do that is I'm going to actually find his kinetic energy. So to use the work kinetic energy theorem, I'm just going to say that the work done on him as he's jumping, at this point the only force acting on him is gravity. So the work done by all the forces that are acting during that portion is equal to his change in kinetic energy. Well, that's the work done by gravity. Well, that's mg delta H. That's how far he's actually dropped during that time. You'd probably recognize that as the difference in gravitational potential energy between this point and that point. Well, that's equal to 1/2 mv final squared, since that would be his final kinetic energy if I chose this as my final position. Now right away you can see that the mass cancels out. It doesn't matter that he's 75 kilograms. A 55 kilogram person would be moving the same speed at this point. And you probably recall that from free fall. Didn't matter what the mass was that we'd be able to get. The speed is independent of that. Now if I want to solve this for v, I would just go v final would be equal to the square root of 2 times g times delta h. And when I plug those numbers in, using delta h to be 20 meters, so how far he's dropped this way, we would get that his speed would be about 19.8 meters per second, or roughly 20 meters per second with sig figs. So that would be his speed. If I wanted to determine his kinetic energy, it would just be mg delta h. But all I asked for was the speed of him. Let's keep going now. He's going to continue to fall, and at this point, as he falls, the cord starts to stretch. So at this point, the cord, he's halfway down, the cord has stretched, and we've stored energy now. There is energy being stored in this cord now, and that's because the cord has stretched a given distance. He's going to continue to drop, continue to drop, continue to drop, until he gets down to about here. So at this point, I'd like to know what is his actual elastic potential energy. And because this cord has stretched such a great distance, from 20 meters all the way down to 45 meters, the actual delta x that the cord has stretched would be 45 minus 20. That would be 25 meters. I can go ahead and compute then the amount of energy that's stored in that band using our EPE equation. First, let's talk about the KE at this spot. Since he's no longer moving here, his kinetic energy would be 0 at the very bottom. His GPE, well, that's a fairly easy equation. It's just mgh. Now, since I'm using the water as my reference at this point, this is my h value. And you can see, based on this here, since the bridge was 60 meters up and he's dropped a total 45, this would just be 15 meters. And so I can go ahead and compute his GPE to be 75 times 9.8 times 15 meters, and that would be his GPE relative to the water below, and that value would be about 11,000 joules. So he still has some energy, some gravitational potential energy at that particular position, equal to about 11,000 joules. And last but not least, there's been a lot of energy stored in that cord, and that's where I'm going to use that 1/2 kx squared equation as we developed before. So 1/2, and then the spring constant is 85 newtons per meter, and that cord has stretched, in this case, 25 meters. And again, the way I got that 25 was by subtracting the 45 from the 20, and we got 25 there. So the elastic potential energy would be about 26,600 joules. And again, with sig figs, I'd probably round that to 27,000. But again, this gives you a way of calculating different forms of energy. Gravitational potential energy, elastic potential energy, and up here, even though we didn't compute it, we could find his kinetic energy at that spot. And so again, the bungee cord, or the bungee jump, really shows lots of different forms of energy. In our next section, we're going to look at how we can use conservation of energy principles to analyze this kind of setup.